Alrighty, you guys. Example 12 is pretty much the same thing as example 11. So if you think you understood it, go ahead and try it on your own, see if you get it right. Otherwise, follow along because we're going to have an awesome time. Alright, guys, remember we always start with the horizontal asymptote because we want to get that done with before we have to factor to find the vertical asymptotes and zeros. Because remember, horizontal asymptotes, we need to know the degree, and once we start factoring things, the degree kind of gets more confusing. So we're just going to do the horizontal asymptote right off the get-go. So let's get going. Alright, so our horizontal asymptote, we must identify the degree of the numerator and the degree of the denominator. So let's see what happens. So degree of numerator and our degree of denominator. Alrighty, so the highest exponent I see in the numerator, well, I don't see one, which means there's secretly a 1 sitting there. And that's our highest exponent. So our highest exponent in the numerator is 1. And our highest exponent in the denominator, well, there's only 1, which makes it easy, right? It's a 2. Alright, so now I have to figure out which rule am I going to use. So our degree of the denominator, this one is larger than the numerator. So I'm going to abbreviate degree of denominator is greater than the degree of the numerator. And remember, when the degree of the denominator is larger than the degree of the numerator, the horizontal asymptote is always y equals 0. So it's just y equals 0. Okay, so I know on this graph there'll be a horizontal line sitting on the graph where it crosses the y-axis at 0, which is our x-axis, actually. So there'll be a vertical asymptote on the x-axis, which is pretty cool. Okay, the next step to find our vertical asymptotes and our zeros, we must factor our lovely rational function. But in order to factor, I must have a degree too, which the highest exponent in the numerator is 1, so I can't factor that. And I can't really factor a monomial, which is in my denominator. So guess what, you guys? I don't want to factor, which makes my life infinitely easier. So to find our vertical asymptote, we set everything in the denominator equal to 0. So I'm going to set my x squared equal to 0 and solve this thing for x. So the way we undo a squared is by square rooting that thing on both sides, which the square root cancels out the squared. So we're left with x equals technically plus or minus the square root of 0, which the square root of 0 is 0. Now the reason why I didn't put plus or minus 0 is because we can't really have a positive or negative 0. Okay, so whenever you square root both sides of an equation, do not forget about the plus or minus. Remember, that's when the demon cats come for you, but the demon cats will be nice about 0 because 0 is neither negative or positive. So our vertical asymptote is simply just at x equals 0. So this will be a vertical line that hits the x-axis at 0, which guess what, you guys? That's the y-axis. So there'll be a vertical asymptote on the y-axis and a horizontal asymptote on the x-axis. So our axes are filled with asymptotes. It's going to be quite divided. It's going to be like this. So it's going to be epic. You'll see the awesome graph in the Prezi. Don't you worry. Okay, in our zeros, we set everything in our numerator equal to 0. And then we'll be done. So we're going to set x minus 1 equal to 0. That's the only thing in the numerator. Alright guys, let's get this show on the road. So I'm going to bring negative 1 to the other side, which the way we do that is by adding 1 on both sides. Negative 1 plus 1 cancels and turns to 0, and 0 plus 1 is 1. So the only place where the graph smacks the x-axis is at x equals 1. That's where our 0 is. So that's it, you guys. We have conquered example 12. Now we have one more like this, example 13, which again, if you think you kind of get the gist now, you can try example 13 on your own and see if you get the right answer in the end. Otherwise, follow along with me and we'll have a wonderful, jolly old good time.